Good afternoon, everyone. This is Jennifer Beliveau, Director of Sales from Applied Math Modeling, and today's moderator. Thanks for joining us online today. We're excited to share with you another one of our popular webinars, Predicting Cooling System Failure Modes in an N+1 Data Center. And with me on the line is Paul Bemis, Applied Math Modeling's President and CEO, and Dr. Magnus Herlin, President of Ansys Incorporated. Before we get started today, we'd like to inform you that, as always, we have a question and answer session at the end of our webinar. You can enter your questions in the question panel that's located on the right-hand side of your screen, and we'll answer them at the end of the presentation. If you're having any technical difficulties with either audio or viewing the presentation, please click on the raised hand icon, and I will respond to you through the chat window. All right, let's get started. Paul?
Thank you, Jennifer. Just a quick introduction to who we each are. Magnus and I'll do, of course, our part. We are Applied Math Modeling. We are a software company, software development company, responsible for the development of the CoolSim application. It is in partnership with the Ansys Corporation. We do use the Ansys solvers and meshers and post-processing. We build the interface itself and, of course, are responsible for the customers and the use of the tool. The tool is a little different than others offered in this market. In fact, anything offered in any of these markets, it is actually based on a SaaS model. So the way CoolSim works is that you pay for it proportional to your use of the tool. Unlike traditional CAE packages where you have to pay for all of it, regardless of how much you use it, here it's a proportional pricing, and it is structured in a way that allows you to pick a subscription that is more cost-effective, more closely aligned with your expected use pattern. And furthermore, all the heavy lifting of computing and meshing and solving and posting takes place on the cloud. So it's a cloud-based engineering simulations software offering. We are actually experts in the field of CFD, and we have spent a long time in that sector doing all kinds of fluid flow problems, and can support you, of course, with the tool. Now, Magnus is also here with me today, and Magnus is an expert in airflow modeling as well, done an awful lot of work in particularly data center work. Magnus, would you like to introduce your company?
Yeah, Ansys Incorporated provides environmental solutions for mission-critical facilities, and we've been doing that for about 10 years now. Before that, I was a principal researcher at Bell Communications Research out in New Jersey, and there was a lot of fun work there. Been focusing quite a lot on CFD modeling, providing a lot of CFD services for the Silicon Valley area here on the West Coast. Also being quite involved in something called DCIM, and maybe some of you are familiar with that technology. That's also a very good tool to understand what's going on in the data center. Okay.
So what Magnus and I are going to do today is take a look at two different designs, and what we're going to be focusing on is this whole issue of N+1. N+1, of course, is the idea that you have enough cooling capacity to be able to handle a failure mode situation or a maintenance situation where one of the cooling units in the room goes down and you're left with the remainder, and you have to understand what's going to happen in that case. So we're going to look at a couple different designs. We're going to look at a traditional raised floor design. It is what they call a perimeter. It is the cooling units are arranged around the outside of the room. They are downflows. The air is blowing down into the subfloor, the raised floor. And in this case, it's going to have a mix of 30-ton and 20-ton cooling units. The second case here is a non-raised data floor design because that's become popular as well these days. These are upflow units. The air is actually traveling up through the cooling unit into the upper section of the room and dropping back down. Here we've got two 30 tons and one 20 ton. Now the goal of modeling and what we're going to show you today is how to predict what happens under these conditions, because unless you have an understanding of what's going to happen when these failure modes occur, then you become surprised by them and in a panic kind of, well, what are we going to do, and roll in the fans and other things. I've seen many different kinds of reactions to these things, but it's just we feel better to know beforehand if you're doing disaster planning or what they call DR planning, disaster recovery planning. It's really quite important to know what's going to happen under a failure condition. And that's one of the many things modeling can do for you. Failure mode, it can also do many other things. We're going to focus just on failure mode today. Now, we're going to be using a few metrics. I've used them before. I'm not going to dwell on them today. We're going to use PUE and DCIE. PUE is power utilization effectiveness. It's really just the ratio of total facility energy divided by total IT energy. And in that numerator, you've got everything. DCIE is the same. It's just inversed times 100%. So if you get near 100%, you're great. 55, not so good. Same thing, PUE 1.2. You want that to go down. So 1.0 would mean that that there is no energy going to the cooling system at all. You got the windows open. 1.2 means, of course, that you're spending a little bit of energy on everything other than IT, etc. So the other metrics we're going to use are RTI and RCI. RTI, we're going to use it here as a ratio of the rack flow rate to the air handler flow rate. You want these matched as closely as you can get them as well. In other words, if you can predict what the racks are going to require, then you can get the air handler to give you just what it requires, just what those racks require, then you've got a perfect situation. You've got a ratio of 1, and everything is balanced at 100%. But if here the rack is getting more air than it needs, this portion is going to decline, and therefore you're going to have net bypass airflow. The air is going to be going around the rack, not through it, and back to the air handler. A problem there is twofold. One, it's a waste of energy. Number two, it reduces the return air temperatures, and therefore the efficiency of the heat rejection system itself. So that's not a good thing. The other case is not as good either. If your rack flow rate is higher than your air handler rate, this thing goes above 100%. You can see here. Now that problem is you don't have enough air coming from the air handlers, and as a result, the rack is breathing its own exhaust back around in a loop. So both of those are undesirable. You want this thing balanced. The other one we're going to use here is RCI. And instead of going over this in a lot of mathematical detail, the rack cooling index deals with whether the rack inlets are conforming to the ASHRAE specification for temperature on the inlet. So you see here the recommended range for most cases, Class I realize these have been starting to be pushed up higher, but most people generally look at that recommended range as a first pass. They'd like to see their rack inlets between 64 and 80 degrees roughly of temperature. And if you're below that, then your rack cooling index is going to be low, and that's a waste of energy. Same thing on rack cooling index on high. If you have any over temperature conditions, then this thing's going to be less than 100% as well, and that's not going to be good. So again, these are metrics we use to optimize the design in the data center. Magnus had quite a bit of work involved in these. You see his reference below. And I think these are very good. I like these because what they do is they allow us to summarize an awful lot about what's going on in the data center with just these 3 metrics. And we're going to use them today to look at a data center. They don't tell the whole story, but they tell an awful lot of the story. And they can be used to very quickly understand what's going on in that data center. So let's take a look at the first case. Here we have a classical room. It's a downflow design. I mentioned this before. It's about 6,000 square feet, 18-inch plenum. You may recognize this design because it's been used a lot over the years. Its total capacity here, 8 CRAC, 630 kW, 180 tons. The IT load here is only 529. So, you know, you look at this and you sharpen your pencil and you go, yeah, N+1. We should have enough extra cooling capacity for this thing to qualify as an N+1 design and to be able to run without one of these units on. Now we have 2 different kind of units in the room. We have 20-ton units and 30-ton units. What modeling allows you to do is understand what happens depending on which one fails, because the things do change. Airflow is very hard to predict without a modeler, and you can't just look at it and say, well, this is going to be fine. Rules of thumb are fairly good in many cases. Here it's very helpful to have a tool that allows you to look at these designs closely. So Magnus, you can help me look through this first one. This is the first design here. This is actually an old IBM Data Center. It's been around a long time. And what I'm doing here is showing this to you inside PowerPoint. Now, a little bit about CoolSim. CoolSim allows you to quickly produce these outputs just like this. You'll see them all formatted the same. The output formatting is automated, and it comes out of the application and can be used in other ways. Here I'm using it in PowerPoint. So all I have done is added a web page to my PowerPoint presentation. Very easy to do, very quick to do. And in this one page, I have everything that has to do with this particular data center. So, I can look around the geometry and see what's going on here. And over here on the left are hyperlinks to various pieces of data that can tell me an awful lot about this room. And I can do it all from this one page in PowerPoint. And the reason I point this out is because this is the most effective way I have ever seen of looking at a bunch of results from CFD runs together. And I've been in this business a very long time, but this is a very succinct way to look at a case. Here I have example-based case number 1. Everything I want to know about this case is here on this one PowerPoint slide embedded with hyperlinks.
Yeah.
Yes.
What I was saying here is that this is a very effective way, I feel, to show, and Magnus, you can comment on this. I think showing results inside of a PowerPoint slide via HTML is a very efficient way to review these cases.
Mm-hmm.
I haven't seen anything like it before. Usually you run into cases where there's one image or two images. It's unusual that you can get all of this in one spot. Mm-hmm. But my question to you was, here's the case, and we see it here. This is a very typical, this data center has been used quite a bit of the years. This is an old IBM data center that was used early on. It's got some cable trays under the floor, some underfloor obstruction. It's got some taped silos over here, angled walls, downflow design. This is what we call a natural convection room in return, in that the air comes out of the tiles back to the cooling units without going through a ceiling plenum or anything like that. But the question I had for you that I wanted you to answer is, looking at this data right here, what does it tell you?
Well, first of all, I would like to mention something. Some people might think that why do we need CFD to figure out how the air is circulating in a data center? And the thing is that to mentally envision what happens when one CRAC unit stops working, it's very, very difficult. Things might happen that you could never have dreamt about. So that's why it's so important to use CFD for design, and maybe not just for design, but for operational purposes too. But the challenge with CFD, though, is that you get a lot of data, and you need to make sense of that data. And all of you've probably seen that you're slicing up the room in different planes, and then you color it according to pressure or temperature or some other parameter. And that's fine if you're skilled user, and you can do a quick interpretation of that plane. But to me, what Paul is trying to do here is he tried to condense all that data into a few metrics and let the user draw the conclusions from that. And here we have CUP, we have PUE, DCIE, RTI, RCI. Not many parameters, not many metrics, but taken together, they're telling a very good story, what's going on in this particular data center. I think this case is with all the CRAC units running.
That's correct, yes.
Yeah, so I'm sure Paul is going to go through these numbers and point out how you very quickly can see if this is a well-functioning data center or not. So the whole idea here is to compress down maybe thousands or tens of thousands or hundreds of thousands of data points into a few metrics, maybe 4 or 5 metrics.
That's right. So what we have here is the few metrics here. COP and PUE we're not going to focus so much on today. PUE of 1.8 is really pretty poor. This is a fairly poor performing room. But take a look at the RTI number right here, Magnus, 84%. Now, what's that telling us? It's telling us that we've got net bypass airflow here, right?
That's correct. If it's below 100%, it means that we have a bypass there. And of course, that's not good, because if you have bypass there, we are funneling through too much air to the space, and depressing the return temperature back to the air handler, so the efficiency of that system will not be at the peak. That's
correct. Now, the RCI high is 99%, which is telling us there aren't many hot spots in this room at all right now with all those CRAC units running. But the RCI is below 0. Now, what's that telling us? That we're way too cold, right?
Yeah, it means that if that number is below 100%, it means that it's too much cooling in the space, somewhere at least.
Right.
And in this case, it's not just lower than 100%, but it's below 0, and that's a very poor performance. Usually, if that number drops below 90%, it is generally considered to be poor.
That's correct. So let's take a little further down in our summary report here. And again, this is generated for every single run. We generate these reports. So here we are with CRAC performance, and you see here, these are the CRACs. You notice they're all running at 60 degrees of supply temp. So they're running very cold. The heat removed is shown here. There's quite a bit of variation in heat removed. You notice that some units are pulling out a lot. These are the bigger units down here. These are the 30 kW units down here. But look at the variation even in the 20K units. We've got one running at 47 here. We've got one running at 62 kW removed of heat. And it has all to do with this return temperature right here. The return temp on this 47 is only 72 degrees. We've got a 12-degree delta between supply and return. And that's largely because this one is running at 12.5 and it's bypassing a bunch of air. Now, to see that, we have a bunch of other plots here, the most important of which that I find, Magnus, is one we've added recently to the solution, and it's called the ASHRAE recommended range. So these are rack inlets here that I'm looking at. Again, I'm doing it all inside of PowerPoint. These are the rack inlets, and I'm looking at temperature variation with respect to this green band. 64 is the low, 80.6 is the high, and we'd like everything in the room to be in that band. It means we'd be conforming perfectly. But the fact that our RCI is very low, less than 0, RCI low, means that we're well under temp, and you can see it here in blue. So the combination of the summary report plus these two plots. Now, if I go to allowable, it gets a little better because here in allowable, you know, the spec is a little broader in both directions, and I get a little more conformance, but I'm still really too cold. Now, the problem here, if we look at the full range, and here what I've done is taken temperature. Again, these are automated. This comes out the same every time. But I've taken full temperature, which ranges from 55 degrees, 55, 56 on the inlet, all the way up to 82. And I've spread color out across it. So you can see the variations. You can see here that it's got some recirculation occurring in several different areas.
And maybe it's good to point out that these planes, the colored planes we talked about before, they are right at the intake to the electronic equipment.
Mm-hmm.
That's what these plots are showing. And I think if you go into that summary report first and you find that something is not right, that's the time to drill down a little bit deeper. And the natural way to do that is to go to these plots where you can actually see where the problems are. But if things are just fine at the summary table, maybe there is no need to go deeper because everything seems to be okay.
Exactly right. Exactly right. And in CoolSim, we give you the summary report as an attachment to an email on when the job is completed. So the beauty of that is you can take a look at your performance of a particular simulation without having to go back into the application at all. In fact, I do it on my smartphone. I'm able to see the output report and study them from your mobile device. which is where I think this whole thing is headed. What these color plots do, although they require you to open something, you don't have to open the application in CoolSim, but you do have to open a computer to view the 3D plot like I'm viewing here. What they allow you to do is see the issue. Where is the issue? You can begin to drill down and see where is the issue. And yes, these are rack inlets, and you can see them. We've only painted them onto the surfaces of the racks. And if you take a look here, you can, in these pathline plots, you can see exactly what's going on. This one is pathline plots from the racks, and what I'm doing here is showing you only the air coming out of the rack itself and going supposedly back to the cooling unit. But you see what happens here in this design, Magnus, we've got a cooling unit over here and a cooling unit over here. So the air is going to come up, and it wants to get back to those cooling units. But on its way, it gets sucked into the intakes of some of the other units. I'll show you two spots where recirculation is occurring. One of them is right here. This is rack recirculation, where it's coming out of the rack, coming back around through this CRAC between the two servers and getting sucked into the intake. Now, the reason it's doing that is it's trying to find its way back to that CRAC unit. But on its way, it gets breathed into the intake. Same case here on this end. We got wraparound right here, where it's going around the end and wrapping and being drawn into the intake. So that's your fundamental problem with this overall design. It's not a surprise to you and I. We're familiar with this. The other thing I wanted to point out here, Magnus, is the bypass over here. This is the CRAC that's not doing much work, and you can see why. There's air coming right back around on the return. Let me show you the supply. Here's the supply side here, and look what's going on. It's coming right out of the tiles and right back to the intake. So we've got recirculation occurring here where it comes out of the tiles and goes around in a circle, not doing any cooling there, Magnus. And that's why we only have a 12-degree delta T over there on that unit.
I think this Paul, I think this points out the important fact that any data center has to start out with a solid design, because if you don't have a solid design from the beginning, it's going to be very difficult to fix it. But say that you have a solid design. For example, in this case, you have real problems that when one CRAC is delivering the intake air to another CRAC, that's not going to be efficient. And you also haven't installed blanking panels, so that there are gaps between the racks. And that's where you just show that you get a recirculation. So those are two challenges, at least in this data center.
Yes.
But when you have a solid design from the beginning, you can fix that with this kind of simulation.
Yes.
But after that, you can improve even pretty good solutions to become even better with these simulations.
That's right. It serves two purposes. For those of you who are operators or in the role of operating data centers, a tool like this allows you to understand what's going on in the room and what's going to happen under conditions. It also allows you to experiment with ideas about how to improve the operation or even how to optimize the set points of the operation. So for those of you designing data centers who are in the design area, it's important to have an understanding of what's going on in the current room you're designing or redesigning or the one you're building to know what's going to happen when it's loaded, particularly in this case for CRAC failure. So let's now go ahead and shut off one of the units. Now, really you want to do an exhaustive study here. You want to go around and shut each one of these off, which we have in this case 8 of them. So we're going to want to shut them all off one at a time and understand the failure modes, and that would take a little longer than we have in today's presentation. So I've selected a couple of these to shut off. Now, this is the one I've shut off right here. This is what we call CRAC 45. The number has no significance. You can see it's off in this representation because there's no red return and blue cold supply. So this is the one that's off. And I'll go right to the summary report again, and I'd like to get people used to looking at these numbers. Now, the RTI here, Magnus, actually went up a little bit, which doesn't surprise us, right? Because in an N+1 design, we're actually got more air usually than we need because we've got an extra unit running in the case one fails. Mm-hmm. So when we take one of them down, and in this case I took one of the 20 tons down, the RTI actually improved, but look what happened here to the RCI. It came down. So what that is telling us is that now, even though our RTI going up, we have a better balance of airflow in total airflow compared to total demand or need by the racks. We are running into hotspots, and we're running into hotspots despite the fact that our RCI low is less than 0, which means we're way too cold. So typical case, I think, that we see a lot. CRAC units running at too cold at delivery temperature, which means terrible efficiency. The energy efficiency here is really quite awful. You see a PUE of 1.8, which means that it's almost taking as much energy to drive the cooling system as it is to drive the IT load. So you're paying twice for the electricity going to your servers, and it's because of poor airflow in the room. And you see here that one of the CRACs is turned off. And if we go back now and look at the recommended ASHRAE range, we see we're in trouble right away. Now, you may say, well, yeah, we're in trouble, but we could probably sustain that for a period of time. And I think that's true. If we look at allowable, you could sustain it for a period of time, and so you may say this is okay. But more than that, I think what we're trying to point out here is that it's important to understand these failure modes so that if a situation occurs where the racks get in trouble, because remember, I'm assuming a particular load here on these racks, and that load may change over time. So these models, I think, Magnus, not only become an operational tool, but become sort of a living, breathing kind of thing that you go back to time and time again to understand what happens under a change condition, right?
Yeah, and also I think it's good to point out that you might have a situation that you had hotspots from the very beginning, and then if one unit shuts off, you can get very severe conditions, and that may be way outside even the allowable range. So even though we didn't see it here, it's very easy to imagine such a case. Right.
So I think it behooves everyone to have a model of their data center. They're handy to have. The people that I know who have them rely on them as a method for improving their decision-making process associated with the ongoing activity in their data center or with their data center design. It becomes something that is attached to the data center, and once the model's built, it's a very handy thing to go back to and to look at. Now, let me point out, Magnus, you've heard this too, there are many who argue that, well, unless the tool is perfectly, representing every little nook and cranny in the data center, then it's not effective. I find this to be not true. My point here is that anything's better than what you've got, which is nothing, right, Magnus?
Mm-hmm. Yeah, I mean, this is it's frog leap. You go from nothing to 80% of the correct answer. That's not too bad.
Yes. These are a guide. These tools help guide your decision-making process. They're not a forensic tool that allows you to measure a temperature and then predict the temperature within a degree F. That's not what we're after here. What we're after is a cost-effective solution, cost-effective tool that will help you in your decision-making process, help you make the right decisions, help guide you in the right direction. These tools will do that. Now, if you want them to be a forensic tool where you can get them to match, you can do it. You can do it with CoolSim. You can do it with many. Fluent's been around for 30 years, and then people use it for that. But the amount of time it takes you to create the model and run the model and do all that is longer, and, it's fine. It's your choice. My point here is that these tools can be very effective very quickly without a lot of manual labor. They've become easy to use. They've become cost-effective, and you can build models. People who buy CoolSim are building models and running models in a couple hours after they purchase the code. And that's the kind of thing that we're driving for here through a high degree of automation. The build sequence is highly automated. Obviously, the reporting is highly automated. and it's an easier to use tool. So here, Magnus, all I'm doing here is now walking around and turning off CRACs and making runs. Now, this is very easy to do. You flip a switch. All you do is open the model or click on this CRAC, open up the editor, flip a switch, close it, rerun the model. That's as easy as that. And it'll get easier in the future because in the next revision of CoolSim, we're going to give you a matrix where you can shut them all off in advance and submit it. We already delivered that once with CoolSim 3, and we'll have that feature again in CoolSim 4 very soon. So let's take a look at this one again. We'll go scoot right down to the energy report. Now here, what's interesting, Magnus, look, we got to 99% on our RTI. Now that's because in this one, I shut off one of the 30-ton units, and that's got a flow rate of 17,000. So I'm bringing these two things together. What is interesting here as well is that my RCI high went to 97%. It improved a little bit over the last run, and the low came up. What's kind of interesting is the low came up. Now the reason the low came up, I'm still shooting air out at the same temperatures, but it has to do with mixing in the room. Because there's less total air, there's only 92,000 of CFM here of total air. I took 17,000 out. Then my return temperatures in my worst case conditions went up a little bit. They were 12 degrees. Now I'm getting those things up now to 14, 15 degrees, that sort of thing in my worst case conditions. So it's interesting. Now if I take a look at my recommended plots here, you see I'm not in trouble at all over in this region. This region is the section here that I'm most worried about. This is the CRAC unit here that's causing me the most pain because it's close to these. Let's go back and look at it in a shaded view for a minute, and I'll show you. It's close to the CRAC, and whenever you're close to the CRAC, you have very high velocity air coming out, and these have turning vanes on them. So very high velocity coming out, and it's hard for the air to make this corner right here, Magnus, right? Air doesn't bend well. It doesn't want to. It's lazy.
Paul, there is another problem with this data center besides these two other issues that you addressed. And the third issue here is that the CRAC unit here is lined up with a cold dial, and that is kind of no in data center business too. It should be lined up with a hot dial.
That's right.
So exactly what you said, you have a very high velocity, especially if you have that turning vane that is not really recommended.
Yep.
You have very high velocity. That means that the static pressure in that raised floor is going to be very low, so there is not much air coming out of those pipes.
Yes. You can see it in these plots here. Again, there's plenty of plots here to look at, but you see the airflow is not that good right in that region. And furthermore, if you take a look at the air coming from the tiles, you can actually see the bending of the air here, and I'll just zoom in tight. Again, this is all, I'm looking at this in PowerPoint, which is kind of a nice, easy way to look at all this data. But you see the bending of the air as it comes under there, Magnus. It actually is trying to get up into this region of these racks, but it's failing to do so. So it just bends. And most of it goes down to the other end. The bad news is I've already got too much down this end, so not really helping me much. But from a sort of a data center optimization point of view, this data center behaves better with this CRAC unit off than with it on, which I thought was kind of interesting. Not something you would predict. Now, it would be important for a full study to continue to go around the room and shut more of these units off as you go, because then you'd get an idea of what each of the failure mode conditions are, and it would give you a feel for where you could add capacity in the room without getting in trouble, which is another important thing to know. If you're a data center manager and your business guys come in and say, we want to drop another 30 kW of servers in the room, they're going to ask you where to put them. And without a model like this, it's not always clear where to put them. But if you do have a model and you've looked around and looked at the different failure modes, you can say, well, I have a pretty good feel it would go, over in this particular section, and let me run a model and see if that's okay. So we have a lot of customers right now, Magnus, who use it as a tool to make sure that, particularly in a colo case, that load can be put in the room without causing major problems.
So Paul, if you go back to that summary table.
Yeah. The PUE. Yeah.
share the summary table, I just want to point out something with the metrics there.
Yep.
So really, and I think that attendees realize now where this is going, and where it's going is actually that RCI and RCI high and RCI low, there's like an interplay between these metrics.
That's correct.
The trick here is to get them as close to 100% at the same time.
Right.
So CFD is a fantastic tool of doing that without taking any risk in the data center.
That's correct.
You're changing things, and you try to get these numbers reasonably close to 100%, and then you have reached a point that you're not wasting energy by fanning around a lot of air. At the same time, you're providing the actual recommended temperatures for the intakes to electronic equipment, and that can be equivalent to reliability of the equipment.
That's correct. That's exactly correct. And they are an interplay. I mean, as you turn down RTI, you have to watch the others. And I think the direction you want to go is get the RTI as close as you can to where it should be. Match those racks as close as you can. Watch the RTI high to make sure you don't have any hot spots. And if you do, go find them with CFD and look at the plots and understand where it is.
Right.
And then begin to drive temperature up. Because by driving temperature up, you notice these are all set at 60 right now. That's a boundary condition I set. But you want to drive these things up as high as you can because it saves energy. You'll get roughly, the metric, Magnus, that's thrown around mostly is about a % improvement in efficiency of the cooling system per degree F. Now, it's not quite that, and it's not always linear, but if you can move the temperature up 10 or 15 degrees, it's going to make a big difference in your annual operating cost, particularly if you've got any kind of economizers at play at all, because it'll open that window for the economizers to operate. So what I did here is I sort of put the plots side by side so you could see them. Now, here in case 1, the PUE actually went down. In case 2, to 1.72, and then went up a little bit here to 1.76. And that's because of the different cooling unit things that we're shutting off. But more than PUE and COP, we're not really focusing so much on that today as we are these other metrics, RTI and RCI. And here what we see is we started off with an RTI of 84, and when we shut off the 20-ton CRAC, it went to 95, so pretty good. But when we shut off that 30-ton CRAC, things got even better. We went to 99%. But the RCI high actually got a little better as well. It went to 93 and then to 97. And then the RCI low came up to 10. So that one came up as well. So you can use these metrics as a way to drive the design, and they work quite well. So what we also did here, I made another run. I mean, this design was begging for cold aisle containment because we had recirculation occurring over here at this end of the room. And so I took 2 tiles out, kept the loads the same, put in cold aisle containment down at this end. These are assumed to be some kind of curtains over here. And I'm just checking my audio. I guess, yeah, I can see that you can hear me, right? So now let's take a look. What I did here is I shut that 30-ton off again over in this region. And I just wanted to see what would happen when we shut that 30-ton back off and went over here and had a look. And you see here my RTI is 92%. That's quite good. My RCI high, 100%. RCI low, 5%. So, you know, things aren't too bad here. If we take a look at my RCI high, which was below 100 prior, now is perfect. So I'm within range. I'm too cold still. So there's an opportunity here to begin to raise supply temperature, particularly the temperature of these cooling units down at this end of the room. We weren't able to do that before because we didn't have enough uniform temperature down here in this room to even give that a shot. But now we're running with one of the 30 tons off. Things are looking pretty good. And there's an opportunity here now with containment to begin to drive up the temperature. But again, I would caution, even in the containment case, it's important to do the failure study to understand when I did containment, did it make my failure mode conditions better or worse? Because I have seen cases, Magnus, and maybe you have too, where you come up with this engineered solution to try to do containment or try to manage your airflow, and you study it in the failure mode, and it's actually worse than it was before.
Well, absolutely. If you don't do it right, just remember that when you do a containment, it generally means that the cold aisle, in this case, is going to be cold, but that also means that the hot aisle or the hot aisles, they're going to be hotter.
Yes.
So if you have any openings now, unintentional openings between the cold aisle and the hot aisle, and you get recirculation, it can actually be a worse situation than you had before.
Yes. And furthermore, in hot aisle designs, there's a human factor issue. I'm showing it here. This is a slice right through the data center at 6 feet. And because the cold aisle is fully contained, it's of course cold, but there's rarely anybody in there. Humans are walking around in the hot aisle because the room has become the hot aisle. And you see here the effect, the temperature, now we're pushing it up into the high 80s, low 80s, high 70s, low 80s. And the cooling units love that because the big delta T across the cooling unit means an efficient cooling unit and a low energy consumption on the cooling unit. However, the human is going to get nervous. So people talk to me a lot about cold aisle design, Magnus, and cold aisle containment. But in reality, when I've seen it used, oftentimes the data center is operating at a much lower, quote, return temperature than it should be because people have turned the CRACs so that the return temperature, which is they're standing in the return aisle, effectively, is low. In other words, the human factor prevails, that people get nervous in the data center when it's hot. So they just naturally want to turn that thing down. And that does have an effect. So I call it the human factor. It's not a science issue. It's not a thermodynamic issue. It's human factors there for cold aisle containment. I tend to prefer hot aisle containment whenever I can get it for that reason. All right. So summary slide on this section, and we're gonna take a quick look at another design as well. But I think the point here is that even though the design may be N+1 on paper, unless somebody runs some models on it, it's unclear what's going to be happening in a failure condition. And over time, if you don't have a model of your data center that is representative of what's going on, and your IT loads change and people move things around, it's unclear that it's going to behave itself in a failure mode. So it's going to depend on which one is down. And I would argue that plans need to be developed and put in place prior to having it, sort of hit you in the face, if you know what I mean, right, Magnus?
Right.
So let's look at another one. Here is another case here, very quickly. This is a non-raised floor design with upflows. This is one I was exposed to not too long ago, and thought it's an adaptation of one that I had seen. So here's the original design. This is a screenshot coming out of CoolSim 4. And you see here, this is a non-raised floor data center, and they've got 3 units in here. These are 2 30-ton units over here, and this is a 20-ton unit here. And they've put these scoops at the top, and they're just blowing the air straight into the top of the room, and the thought is that it will come across and fall down, because of the weight of the air. It's cold, so it's going to drop and fill that room. And
at least on my screen here, I can't see that slide. Maybe others can, but I can't.
Jennifer, can you see this slide?
Yep, I see your slide. Yep.
Okay.
Okay, maybe it's just my screen.
Might be a slight delay on your side.
Sure.
GoToMeeting's not perfect, although it's a great tool. So let's take a look. This is a set of results from that in case you're coming, and I'll just leave it here for a moment. And what I'm going to do is first show the airflow from the cooling units in this case. And here, Magnus, let me know when you can see this, but I've got very high velocity air shooting across the top of that room.
Mm-hmm.
And the problem you have in these kinds of cases is, again, that high velocity air is shooting across and it's not getting to those units that are close to the cracks. Again, it's distribution of air. If we had our way about it, we would dump this air all sort of in laminar flow, you know what I mean? We'd let it all come very slowly in high volume, but very slowly to all of these units concurrently. But, you know, the world is not perfect, and this is what happens. So let's take a look at our summary report again, and we'll shoot right down to this data energy report section. And you see here the RTI in this room is 59%. Now, the RCI high is 100%. So everybody's happy in terms of cooling. Nobody's too hot. RCI low is 100%, which means, you know, we're not too cold. So, I mean, at first blush, you would say these are pretty good statistics. That we've got both high and low at near 100%. Tell me what's wrong. Well, what's wrong is the RTI is 59%. So the amount of energy being dumped into that room is extremely high compared to what it needs to be. And in this case, we've got one of the units off. So now this may be a design where, you know, it's not loaded yet. I don't know about this one, but, you know, as you begin to load this design, things are going to change as well. So if we take a look at the full range of temperature here, you can see the problem that is going to be the case in this design. That these racks over here near the cooling unit aren't getting really much cold air. You see their temperatures are higher. The distribution, this is a full distribution of temperature, so the low on the rack faces, on the rack inlets, is 66 degrees. The high is 81 degrees. And you see the highest temperatures sensed on these rack inlets are the ones closest to the CRAC units. And I often find this. I find that the units closest to the CRAC units are the hottest because the air is rushing by either in one direction or, in this case, is also being sucked back to those inlets. Returns. The returns are at the bottom. So let me show you that here in one of these plots. Here I'm going to look at path lines, which is they're sort of particles in the air that are coming back to the cooling units. And you see here what's happening is the hot air is coming out of these units, coming out of the hot side of these units, and they are arranged in fairly good order. I've got a cold aisle here down the center. I've got a hot aisle here. They're all facing correct. But look where the cooling returns are here on this one, Magnus. They're down at the bottom. If I turn this model around and look at it, you see what's happening. The hot air is moving up because it's hot, so it's buoyant. It's moving up. The buoyancy is causing the air to rise. It's mixing with that cold air that's shooting out, and then it starts to come down and get sucked into those returns. But during the intake to the return, it's going right by the rack inlets, and it's changing the temperature there. So if we were to look at a cut plane here at 3 feet, we would see quite a bit of color variation there. So we don't have very good return. The return path here is too cold. This should be warmer right here because I'm 3 feet off the floor. And so my temperature variation on these cracks is not that good. It's not as good as it could be. So this is, you know, yet another situation. And if we roll forward and we say, okay, well, what happens in a failure mode here? Now, this particular run, I'm shutting off one of the 30 tons. I'm turning on the 20 ton to compensate for it. I'm assuming these are networked together and one goes on and one goes off. You would say, well, I should be okay in this case. This one should be a fairly good case. But let's take a look at what happens. Not so bad. That one does work okay. Let's take a look if we shut off the other one, the other 30 ton. What happens in that case? And in that case, we got problems. So sometimes it's just the opposite of what you think. You would think the one here might be the problem, but it's not. It's the one over here that's causing the problem. And the reason, again, Go ahead.
I just want to point out that this just demonstrates what we touched on before, that to think that we can predict everything's going on in a data center when one unit shuts off is a very, very difficult task.
Yes. And it's not immediately evident why. So having a tool that allows you to try it out and study it before the condition occurs is a handy thing to have. Now, as it turns out, if we take a look here, Magnus, at the airflow, what we find is it sort of becomes evident to us why this case is dangerous, why this case is causing problems. You can see right here, this is the air coming back. We're looking here at air return. It says right here, temperature return. And the air is coming out of this hot aisle, and it's got nowhere to go. So it has to go up over the top and around this aisle and get sucked into that intake down low. And of course, during that process, it gets sucked into the intake of these racks and drives those rack temperatures up. So here, it's not so much supply problems as it is return problems. One of the things that I've noticed in non-raised floor data centers is the returns are often the problems, because as design engineers, we often think of, well, let's get the cold air to the racks. But just as important is getting the hot air back to its proper place. Like you mentioned earlier, you should line up your hot aisles with the returns of the CRAC units so that they can breathe. So again, if we take a look at this report, it's likely going to be telling us that we've got problems. And yes, you see here my RTI dropped down because I pulled out that 30-ton unit that shut off. RCI high dropped to 73%. RCI low 100%. So you know I'm not too cold anymore, but you know I've got problems with hot. So if I go down and take a look at my report, I'm going to find a lot of failures here. My highest rack inlet temp is 96 degrees, which is not a healthy thing. I don't even think I'm falling within my allowable. Yes, look, I'm not even falling within my allowable range, which is up to 90 degrees. So we've got problems in this data center. If this unit goes down for any reason, maintenance, belts, any reason, this data center is going to be extremely hot. And if we take a look at any of the cross sections here, let's say at 6 feet, we're going to find this data center is warm. I mean, it's showing it to be upwards of 110 degrees on the hot side. It's going to be, you know, in the 90s in this section of the room. That's going to cause failure mode conditions to exist.
So, Paul, maybe another thing to point out, you've been looking at failure scenarios here, but everybody can probably realize that or envision that if you want to optimize those metrics, the RTI and RCI, it's going to be a little bit dancing around to get to the optimal solution. And then the next question would be, why don't we do that automatically with the CFD tool? Let the tool optimize this by dancing around and coming down to an optimal solution. So would you like to say something about that?
Yes, I think there's an opportunity to do that, Magnus. I think with the tools, with the CFD tools, there is an opportunity to create and model and predict the optimal operating point for any data center using an iterative process. And particularly the way we've set up CoolSim with cloud computing, we did it that way on purpose so that you can run multiple scenarios at the same time to understand which scenario is best for your data center. Now, Magnus, this is true of all data centers regardless of type. In other words, variable speed fans, the whole thing, all data centers will have an optimal operating point where the fan speeds are correct, the cooling unit is correct, the temperatures are correct for that given layout. Okay? So you give me a geometry layout, however it's laid out, and we will be able to find for you the optimal operating point through scenarios like this, scenario modeling, where you say, what is the optimal point? And I think you could go into a data center and configure it that way and get very, very close to being right where you want. And Magnus, I would argue that as we move towards these control systems where we have sensors under the floor and sensors here and sensors there that are all, by the way, on their own, sensing something and controlling fan speeds based on that, that the idea of knowing what the optimal design point should be when you enter the room to set that stuff all up is going to become critical, wouldn't you think?
Absolutely.
Yeah.
Absolutely. That would be important to any data center.
Any data center. Whether you've got variable speed fans, fixed speed fans, whether you're turning CRACs off, whether you're doing failure analysis and trying to understand the failure condition, it's important to use a tool like this to understand exactly what those conditions are going to create for you as an environment prior to encountering them. It just happens to be we fixed this, we built this application to be able to do that more cost effectively than others, because you can run multiple jobs on this thing at the same time without penalty. But today our primary mission, I think, was to point out that just because the design says N+1, just because you have N amount of cooling in kilowatts or tons or whatever that's beyond what you need today, doesn't mean you're going to be safe in an operational state. That it's important to understand the failure modes and what they look like, both in terms of optimizing the data center for operations day to day and also understanding what happens in a maintenance mode or a failure mode. And having a tool like this allows you to understand that. I understand some of you are reluctant because it takes a little time to build the model. We'll build the models for you if that's what, I don't want model building to be the constraint, because they're fairly easy to build. You can build them pretty quick these days with tools like CoolSim. So I would argue that understanding it and having a tool like this is an important piece of your overall operational arsenal. And I'm seeing more of it all the time. I don't know about you, Magnus, but I am seeing more of it.
Well, absolutely. I think these summary tables you have, it's going to make the process so much easier for a user.
Yep.
He can focus on the most important, and if he needs more information, he can dig into your comprehensive tables.
That's right. So let me open it up for questions here, Jennifer. If you're willing to host the questions for us, that'll be great. I have our contact information here on the last page in case any of you want to contact us about anything. Jen?
Sure. Okay, just a kind of a comment. Normally I use in my calculations CFM, delta temp, delta humidity, dry and wet bulb temperatures, and also rack temperatures from sensors in the rack. Is this similar to the scenario that they're seeing? And usually plots in advanced physio.
Yes, but I didn't hear him say a CFD model. I mean, sensors are great, but sensors tell you what's going on now. Sensors can't predict the future. So the combination of sensor data and a CFD model is the perfect combination, because the sensor data you can use to calibrate the CFD model. So I build a model of the room, and then I run a simulation, and I use the sensor data to compare with the predicted data that the model is telling me is occurring, and therefore I'm able to calibrate the current state. Once the current state is calibrated, I can then use the CFD model to push into areas that I can't do in the real world, such as shut things off, turn things down, move things around, increase loads and see what happens, that sort of thing. So the combination is important. I think sometimes sensors get oversold because they're the quickest thing to do it. Let me know what's going on. Of course, it's important to know what's going on, but sensors can't predict, and that's the difference. Okay.
Yep. All right. How did you set the airflow that passes through by the racks?
you set it based on, you know, assumptions. We have to make some assumptions, and the assumptions we used in this model was that you need about 156 CFM per kilowatt of power in order to keep the delta T at 20. The basic equation that governs that is that the heat transferred by the electronics equipment is equal to the mass flow rate times the density of air times the delta T. So the only two variables, if it's a 2 kW piece of equipment or 5 or whatever, the only two variables you have are mass flow rate and delta T. We constrained the delta T in this case to 20 degrees to be conservative. Now you can set it wherever you want. You can set it for 30 degrees. Many servers today allow 30-degree delta T's. But if it's 30 degrees, the mass flow rate is going to be lower. Okay, so we assumed that it was 20 degrees, so the mass flow rate is a little higher, a little more conservative. And, you know, that's how we did them. But, yeah, you have to start with some kind of assumption somewhere. Okay?
Okay. What input data is required for the CFD simulation?
Input data, well, you need the geometry of the room. You need to know where things are, okay? You need to know the physical sizes of things, the size of the underfloor, the size of the returns. You know, you need the geometry. You need, because air flows in 3D space. Beyond that, you need to know the CFM of the cooling units themselves, which you can get from manufacturer's data for the most part, or you can measure it using sensors. And you need to know the loads in the racks, which you can measure or you can assume. If it's a brand new design and it hasn't been built, you have to make some assumptions about what the loads are going to be. If it's an existing design that's already there, you can go out and make some sample measurements and understand what the loads are in the racks. There's an awful lot of branch circuit monitoring going on right now where you can actually read what's in the rack in terms of load. So you use what data you can get your hands on. Okay?
Sure. How about hybrid cooling, air and liquid?
Air and liquid. I don't know where the liquid is, Magnus. Would you? Where's the liquid?
Well, if you, I mean, I think it's becoming more and more common to have liquid cooling inside a data center. You don't transfer the heat away from the equipment by air, but by a liquid, maybe usually water.
Yep.
So if you're having a liquid cooled solution, you don't have to analyze the airflow rates in the space itself. So, you know, if a part of the cooling is done by liquid cooling, that could be a boundary condition as any other boundary condition in the data center.
Yes.
And then you do the air cooling with the CFD modeling.
Right. Yeah. Liquid cooling is not a new idea. Liquid cooling's been around since the supercomputer days, and liquid cooling is a fine way to do it, but it's a little more expensive. You need plumbing, and yeah, if you've got it, it's great. If you can afford it, it's great. I don't see a lot of it, Jen. I probably see a little more than I used to, because now you see things like rear door heat exchangers with liquid going through them. But you know, it's not a panacea. You've got to get piping out to the units. You've got to hook them up. You've got to worry about leaking. A little more complicated of a solution, a little more costly of a solution, but it works.
And then the follow-on to that is, what about the temporal dynamics of the heat dissipation?
What about the temporal dynamics of the heat dissipation?
Well, the server is not generating the same. Maybe they have different workloads throughout the day. So that means then, consequently, that the heat load coming out varies over a day. Mm-hmm. Well, that is, of course, is a complication for any kind of cooling solution. But you know, I think if, say, for example, you're going to design a data center, a CFD tool is a perfect application for a CFD model. Then you have to assume certain normal conditions in the data center, and that should cover the range of heat loads from the electronic equipment.
Mm-hmm. Yep. I mean, it does change over time. This the data center is a transient environment. We're modeling it here as steady state, but it is a fully transient environment, and you have two choices. Either you can model all of the various transient states or the various things you're worried about. What's the high load? What's the low load? What's the medium? And have those in mind. Or you can take the extremes and just make sure that your extremes are okay, your extreme low case, your extreme high case, what we used to call the corners of the design, and make sure they're fine. Whichever you want. Yep.
Just the additional comment was that liquid could also mean liquid rack doors.
Yeah, I mentioned liquid rack doors. Yeah. I see those. Those are popular. As Magnus pointed out, when you got a liquid door in place, yeah, you leave it. What I would do is model the delta T across it as being different, or the load in it as being different, but there still is air coming out into the room, but it's just a different temperature entering the room, and do it that way, and leave the rest of it, unless there's doors on all the equipment. And if you've got a fully containerized data center then there's no need for CFD. Somebody's already done the CFD when they built the container, I hope. So, okay.
Just too sure.
Yeah.
Well, I don't think containers becoming popular in certain circles too, but you fill those containers. It's not a static environment. The equipment is going to be changed out, and the conditions going to change. So even inside a container, that there is a need sometimes for a CFD modeling to understand really what's going on with the new configuration.
Yes, that's true. Okay, Jen?
Yeah, and then just a comment from one of our valuable users is one important note on iterative processes to find an optimal data center environment is doing it for varying load steps, such as when the data center is at least 25% of capacity, 50%, 75%, 100%, etc. That sometimes people forget to keep track of where they are in terms of mileposts and think the model says I'm fine. If you were to use a 25% load model and be at 35% in reality, you could have a false sense of comfort. And then there's a smiley face. So thank you for that comment.
Yes, and he's absolutely right. You have to assume something about your loads. Now again, let's get back to the transient just example for a moment. The loads are transient, Magnus, right? I mean, a computer doesn't consume the same amount of energy at 25% load as it does at 100% load, right? So we have a variety of dynamic things going on in the data center. When your data center is first built, it's unlikely you're going to have full load in it. So it's important to understand that state. How loaded are you, and model that. Then later on, you're going to get to a different state where you've got 50% loading, for example. It's important to know where the difference between 25 and 50 went in terms of where to put that load. CFD can help you there. A model can help you there. Then you go to 100%. How does that work? And the efficiency of the data center will change over that range as well. Generally, more loaded data centers, heavily loaded data centers, are more efficient than, from a PUE point of view, than underloaded data centers. And there's been quite a bit of talk about this. My PUE is low because I'm only 25% loaded in the data. My PUE is high. My efficiency is low because I'm only loaded 25%. So yes, I agree. It is important to understand where you are with respect to the total capacity of your data center and how much of it you have loaded. And understanding the optimal operating point at those conditions is key to getting good efficiency out of it, whether you're turning units down or using variable speed fans or whatever it is you happen to be doing. All right, anything else, Jen?
Yeah, there's a couple more questions. Why delta T of 20 and why not 10?
10. Well, if there's a delta T of 10, then my mass flow rates would be even higher. So, I mean, you could run them at 10. That's fine. It's just a variable. It's a boundary condition. So if you want to set the delta T on the racks to be 10, you can, or the equipment to be 10. But it means your mass flow rates will be higher, and you've got to deal with that. So, yeah, that would be fine. You can model that.
Okay, and then a follow-on just from what type of input information is needed for the model. How do you input underfloor cabling and obstruction?
You put stuff under the floor like blocks and pipes and other things. In CoolSim, you have general geometry that you can put under the floor to try to represent the blockage. That's the best you can do. It's difficult to lay a cable in a snaking kind of fashion and then generate a mesh for it today, because the mesh count would grow very high and the model would get big and slow down in terms of processing. So what we do is we put blockage under the floor to represent the cross-sectional area of the cables. So if you look at it from a perpendicular point of view under the floor, for example, if it was a raised floor design, and you just put blocks under there to represent the blockage in the cross-sectional area. That's all. Okay.
Yep, and then just lastly, is CoolSim software free? And, you know, unfortunately, no, it's not. But if you are interested in taking a closer look at the interface or talking about licensing options, feel free to get in touch with us, and we will certainly provide you with some licensing costs, or, you know, learn a little bit more about your data center and see how we can help you.
Okay. Well, I want to thank you, Magnus, for being on the show with us today. I appreciate your input and your willingness to participate in today's show, and look forward to working with you in the future on various things, and hope you have a good holiday weekend.
You too. Thanks for inviting me.
And Jennifer, thanks to you for hosting today, and we'll be signing off now.
Excellent. Thank you, everyone, for attending. We look forward to having you online with us at a future webinar.
Thanks. Bye.